open loop, you may experience some oscillations and you will not reach steady state. That's what he thinks. And maybe Siddharth, you also did not agree. What are your thoughts? Why do you think the converter may not reach steady state? Siddharth, can you unmute and speak? We are not able to hear you. Siddharth, you're not audible. Maybe I don't know if he's having an issue with the microphone. So Shubham Roy, Siddharth, can you comment? Shubham Roy, can you unmute and speak? Why did you not agree with the original statement? Or what is your argument? You guys have to respond, okay? Otherwise, I mean, there's no point. Naveen, can you comment?
Sir, as actually Samprit pointed out, I also think that if the load is not connected, then
Hmm.
because of the discharging and charging, like it will be happening continuously. And also, I believe that if the discharging is not happening, then it may not reach the steady state since it will go unstable, like charging continuously.
So Sambit was talking about the possibility of certain oscillations. So you
Yes,
are
sir.
talking
Since
about.
if the R is absent, then in case there can be a scenario that the inductor can keep on charging.
So you are talking about a scenario where it will continuously keep on charging, whether it be the inductor or capacitor. So system
Uh,
will not reach it. It's slightly different than the statement that Sambit kind
yes,
of.
sir. Yes, sir.
uh,
What he mentioned was a sustained oscillation. I believe like maybe there could be a scenario of unstable oscillation.
so you think unstable oscillations? Huh?
Yes, sir.
Okay. So both of you are thinking that there are going to be oscillations. One of you probably sustained oscillations or bounded oscillations. The other person is thinking unconstrained or unstable kind of oscillations. Shubhangi, can you come in?
Sir,
Ah,
sir, in case of Arun this side, in case of
yes.
boost converter in no load situation, the capacitor will keep on charging and have no circuit for discharge.
Okay.
So there shouldn't be any oscillations.
Yeah, but what will happen to the out? Will the system reach steady state? Will the converter reach steady state?
No, the capacitor voltage will keep on rising.
Okay. So now we have three arguments. Okay. I mean against. So some people think that the whatever be the operating condition, whether it be CCM, DCM, the converter will reach steady state. So some people disagree, and there are three arguments. So some think that there could be oscillations, stable or unstable. Some think that the output voltage could keep on rising and it will never ever reach a steady state. So let's uh, you should think of all the topologies. For all the topologies, the situation is not going to be same. It's going to be a little bit different. First of all, let's try to address the problem of oscillations, right? So typically when you choose the LC filter, the L and C values, right? If you look at the cutoff frequency of that LC filter, here the L and C are not together, they are separate. But if you think of it for a moment as an LC, and if you look at the cutoff frequency, 1 by 2 pi root LC, typically it will be much, much, much lower than your switching frequency because you don't want any resonance happening within a switching period. You don't want any oscillations within a switching period, right? That is why when you are analyzing the buck converter, you are not really looking at the LC filter oscillations and all. You are just assuming that this capacitance is a voltage strip element and you are just looking at the volt seconds across the inductor or you are looking at the voltage across the inductor. The reason why we are able to do that is because we have selected the frequency or the cutoff frequency such that we don't expect any oscillations within the switching period. So if the frequencies are far apart, well separated, you will not ideally see oscillations, right? At least because of the LC resonance. So the oscillations are coming because of some resonance, LC resonance. There are other oscillations also which can come because of parasitics and all. But at least whether this filter, these L and C components will cause a resonance. That is the first point that we want to address. So typically they will not. There are certain cases, I mean, depending on whether you're using bidirectional switches and all, and the initial conditions, there are certain cases where you might see oscillations for some time, but normally you would not observe. So the oscillations, because of the well, I mean, the frequencies are well separated, the switching frequency and the resonant frequency. So that understanding that you might see oscillations may not be very valid. So now the second argument, again, the thing is that okay, let's take the boost converter because you're currently working with it. If you remove this resistor, let's try to understand what happens. Let's explore what Arun said a bit. So he said that this capacitor will keep on charging. So why did he say that? I mean, does the class agree with his statement, or do you have any counterpoints?
Sir, if it is an ideal capacitor, then it is true. But the capacitor will have certain voltage rating, and if that is exceeded, then the capacitor will fail.
Correct. So let's first assume ideal components, then we'll bring in practicality. So you can lower your hands. The previous, I mean, those who have raised your hands for the previous statement, lower your hands. And Aditi, can you come in? Aditi, what do you think? I mean, so Arvind seemed to agree with Arun. So what are your thoughts? Nandana, can you come in?
Sir, in boost converter, if load is not there, there is a no path for capacitor to discharge. So the circuit may go to unstable, I think.
What do you mean by unstable?
Means the voltage rating of capacitor may exceed.
No, but what will be the nature of the voltage? Because instability, I mean, there are different types of instability. So what type of an instability are you referring to?
Um, mm,
So, Anushka, this side. So,
Huh.
energy across the inductor should be equal to energy across the capacitor if the load is not there. So, if capacitor is not absorbing that much energy, that it will uh, go to breakdown condition.
What do you mean by breakdown? The-
Capacitor would lose its capability. The
So you have to be a bit more clearer. So you're talking about certain energy, but again, the fact is that I'm continuously switching. Okay, the only thing is that the load is not there, but I'm switching this converter at a particular duty ratio, whatever that be. So in every cycle, the inductor is getting some energy. I mean, whenever the switch is on, the inductor is getting charged, or the energy is being stored in the magnetic field. When the switch is off, that energy is kind of being dumped into the capacitor. So,
but
so in every
energy balance should be
Hmm.
established between the capacitor and inductor.
So the volt second or the charge balance that is required for reaching steady state. So in this case, will you have volt second balance or charge balance when you don't have a load?
It should be there, but if load is not present, so it can fail. I
Hmm.
think so.
Yeah. Any other thoughts? Anybody else want to pitch in? Deependu, what do you think? Pratim, your hand is raised. Do you want to make a point? Deependu, go ahead.
Yes, sir. I don't think the whole second balance will be maintained there.
Okay. So Deependu thinks that the volt second balance will not be maintained. So again, let's try to look at the situation. If unless any of you have any final remarks to make. Yeah, if you have any remarks, just unmute and go ahead. Don't wait for me to call you.
Sir, if load is not connected, then capacitor will not have discharging path.
Hmm.
So it will keep on charging.
Okay. Yeah. So you are talking about which topology? Buck boost. Which topology?
That boost converter.
Boost. Okay. So let's take the boost converter itself. When the switch is on, you are charging this inductor, right? You are applying VDC across the inductor. So whenever the switch is on, the current in the inductor is going to rise. There is no question. Right? You are applying a positive voltage across the inductor, the current will rise. So now when the switch is off, the diode turns on because the inductor will kind of forward bias. The rest of the circuitry will forward bias the diode. The inductor current has to continue to flow. It cannot suddenly stop, right? Because previously there was some current in the inductor. So the moment you turn off the switch, the diode turns on and this capacitor will start getting charged. But like many of you rightly pointed out, there is no path for the capacitor to discharge now. So the capacitor voltage will keep on building up. So in every cycle, the capacitor voltage is changing. So there is not going to be a volt second balance across it will never reach a steady state because the capacitor voltage will keep on increasing and there is no path for the capacitor to discharge. So if you look at the capacitor in all the states, it's only getting charged. Like when the switch is on, this capacitor is just floating. I mean, there is no current in the capacitor. When the switch is off, the capacitor is getting charged. So always there is current in one direction in the capacitor. So the capacitor voltage will keep on increasing. And like many of you rightly pointed out, you will reach a point where things start failing in the circuit. Because when the voltage rating exceeds, depending on that voltage stress is also coming across the components in your circuit. Because when the switch is conducting, this capacitor voltage is applied across the diode, right? So the diode can fail, the capacitor can fail. So different elements will start failing eventually. So that is why in the lab also, when you're running your boost converter, you should never ever run it without load. You should always connect a load and run. But what about a buck converter? Here also, if you don't have a resistor, there is no capacitor discharge path. So will you see the voltage rising in buck converter also?
No, sir. It will rise up to the input voltage, and then it will this circuit would get kind of saturated. So
Why?
there
Could you
won't be
elaborate
any
around?
inductor current. So in buck converter, if there is no resistor load, means there is no load, open load scenario, the capacitor would the voltage across capacitor would keep on rising till V in. And as soon as Vin it reaches that point, there's no more current in the inductor. So it again becomes steady state.
So Arun thinks that for the buck converter, there is a steady state. Even if there is no resistance, there is a steady state. So anybody has any opposing views? The class agrees to that statement, it's okay, but I want you to think about it. I don't think many of you have thought about it, and some of you are not speaking up. But you should think about the points that Arun said. Arun made a very specific statement that there is a steady state in buck converter, and the worst case scenario is when you don't have a load, the capacitor voltage will keep on increasing, but it will only reach up till the input voltage, and after that it will stop. The capacitor voltage will not increase further. So I want the class to go back and check this statement. You verify whether it is true. And you also think of the buck boost converter. You think of the buck boost converter when it is operating in the buck configuration. That is, let's say there's a duty ratio constraint, right? So when you don't have a load, when it is operating like a buck converter, what is the implication on the output voltage? When it is operating as a boost converter, what is the implication? I want the class to go back and check. You can either logically come up with a argument, or if you are not able to come up with a logical argument, try simulating that circuit and then try to explain what you're seeing physically. So that is, yes.
Sir, in case of buck converter,
Hmm.
I guess the capacitor voltage will rise to VDC, and
Hmm.
after then it will be oscillatory in nature. With the offset of VDC voltage, it will oscillate around.
But what do you mean by this oscillation? Do you expect it to be at some frequency?
Yes, sir. It will be the frequency. Yes, sir. And the frequency should be 1 by root LC, maybe.
Check that, because that is what I was saying. The cutoff frequency of the LC filter is chosen to be much lower than that of the switching frequency. So within a switching period, can you see oscillations? Or there is also a possibility that you might see a low frequency envelope or something, but check that. At least these are very fundamental concepts and you should be very clear. I mean, typically boost converter is what people talk about because it's easy to say. Boost converter, if you don't have the load, you know that it's very easy to show that the capacitor voltage will keep on charging. But for the buck and the buck boost, there are some interesting aspects. So look at that. And if you have doubts, we'll discuss it again on Monday. But I want to move on because we want to cover some breadth of topics. So Vandana, I am trying to indirectly answer your question. So did you get the answer to your original question?
Yes, sir.
So there are situations where the converters will not go to steady state. One example is if you are taking a boost converter, no load condition. So it will not reach a steady state. So it is possible. And these are conditions that you guys might accidentally emulate in the lab also. It can be dangerous. Your circuit will fail. So make sure that the load is always connected when you're running the boost converter.
Yes, yes.
So we'll move on.
Yes.
So now let's take the buck converter. We have already looked at the continuous conduction mode. We have dealt with the analysis in some bit of, detail yesterday. So this U is kind of like this. The notations are slightly different because I've tried to match it as much as possible with what I'm discussing in class, but I've taken many of the figures from Professor Ramanarayan's course notes because I was hoping to give a physical lecture. I did not have slides. I had to put together slides very quickly. So I took many of the diagrams from Professor Ramanarayan's notes and the notations are slightly different. I've tried to change wherever possible, but some notations, it could be different from what I usually teach in class. But again, the thing is, for clarity, this is the switching function that we looked at yesterday. So when the switch is on versus when the switch is off. So when the switch is on, the inductor current is rising, and when the switch is off, the inductor current is falling. And there is an average. This average is nothing but the load current, because if you apply charge balance in the capacitor, you will see that the average inductor current is nothing but the average load current. And again, if we apply small ripple approximation in output voltage, this small letter V naught refers to instantaneous values, but if we apply small ripple approximation, I can replace this with capital V naught. And input, if I assume that it's an ideal source, I can replace this with capital VDC. And again, if let's say the conduction is continuous, what do you mean by continuous conduction? So there is typically a misnomer that students think that if the current is continuous, then it is referred to as continuous conduction mode. So that is not entirely correct. So here, yes, of course, the current is continuous, but it is called continuous conduction for a reason which will become apparent eventually. But it just means that the conduction is continuous. It has nothing got to do with the continuity of the current waveform. So this we have seen. We know how to analyze this mode. What will be the slopes of these segments, these line segments? That is the only part that we did not explicitly talk about. In this DTS, what is the slope of this IL waveform?
VDC minus V naught by L.
VDC minus V naught by L. And here?
Minus V naught by L.
Again, it's basic voltage across the inductor, right? So we know the voltage across the inductor. So these slopes are also well defined. And then if you know this inductor current, you can find every other current in the circuit, right? You can combine this with the switching function. So if you just multiply it with the switching function of the switch, you get the current in the switch, and the current in the switch is same as the source current. If you multiply it with the switching function of the diode, which is complementary to this, you will get the current in the diode. And if you take the ripple component, if you subtract the average from this, you will get the current in the capacitor. So if you know the inductor current, you can actually find the current in every part of the circuit. And then you can apply, let's say, volt-second balance to get the voltage gain of the converter. You can apply charge balance to find the voltage ripple in the capacitor. This we have covered yesterday. So now, what do you think will happen when I change the load resistance in the circuit? What do you think will happen to this waveform? Everything else remains constant. Let's say the input voltage is same, duty ratio is same. I'm only changing the load resistance. So what do you think will happen?
the average current will be lowered, sir.
The average
The
current will change, right? Depending on whether I'm increasing or decreasing the resistance.
ripple will be same, sir.
Yeah, the ripple should be same as long as the voltages are unchanged. So ripple will be same under certain, I would say, operating regime. As long as we are considering an ideal converter, as long as the voltage gain is defined by, let's say that Vin is equal to or VDC is equal to D into V naught, which is true for continuous conduction. We'll discuss. We are trying to go to discontinuous conduction, but as long as you are in the regime of continuous conduction, your voltages are not changing. Even though the load resistance is changed, the current waveform will only move up and down, but the voltages are stiff. The voltages are unchanged, the ripple will not change. So the ripple will stay the same. Only this current waveform will move up and down. And eventually there could exist a critical condition, critical value of resistance, where the current just touches zero. Right? So this condition is referred to as bound. All of you can imagine this, right? There is no confusion. So this condition is referred to as boundary conduction because the current is just touching zero. The current waveform is still continuous here, even though whether it be here or here, the current waveform is still continuous. But this is called as the boundary conduction. And this is called as a boundary because this is the boundary between, let's say, one mode, the continuous conduction mode and the discontinuous conduction mode. We'll see what discontinuous conduction mode is in a moment. But here also the analysis, whatever analysis that we have discussed in class, it is equally valid because this is also, you can categorize it as a part of continuous conduction itself. You can apply volt-second balance. You can find the voltage gain of the converter will also hold good here. Current is anyway continuous and the ripple is going to be exactly identical. Even though these are two separate figures, don't worry about the scales. If I'm just changing the resistance, the ripple is going to be identical. It's only going to get shifted. So this waveform, the average has reduced and it has these points, the value points have just touched zero. That's all. So this is referred to as boundary conduction. And then if I further increase my resistance, so what I'm doing is I'm increasing my resistance. When I'm increasing my resistance, the average current is dropping. So if I further increase my resistance, what will happen? So that is when we go to what is referred to as discontinuous conduction. So here also, if you look at the waveform, we can say that the waveform is continuous because the waveform has a value, it stays at zero, right? So the waveform is still continuous. So you should not confuse it with the continuity of the current waveform, but you should rather look at the conductivity of the switching elements. Is the switch conducting, whenever it is supposed to conduct, or if the diode conducting whenever it is supposed to conduct. That is, when the switch is on during that entire interval, there is current through the switch here. Here also it is true. When the switch is turned on in that entire interval, there is current through the switch. But when the switch is turned off, there is a duration for which no element conducts, no switching element conducts. So the conduction, that is why conduction is discontinuous. That is why it is referred to as a discontinuous conduction mode. Diode conducts for some time, but when the current hits zero, then it stays at zero because the current cannot go negative in this circuit. In this circuit, the current cannot go negative. The switch is off, and so the current stays at zero. And there is a duration where no switching element is conducting, and that is why the conduction is said to be discontinuous. But as far as the waveform is concerned, it is continuous. So I want that point to be clear. So don't say that when the current is continuous, it is continuous conduction. When the current is discontinuous, it is discontinuous conduction. So that definition is strictly not correct, though many books and all use that kind of a definition. That is technically not very accurate. So now the challenge is, now we have three modes, or three states. Here we had two states, when the switch is on, when the switch is off. So when the switch is on, we know what is the voltage that is applied across the inductor. When the switch is off, we know what is the voltage that is applied across the inductor. But what about this condition? So when the switch is on, you are applying some voltage across the inductor, so the current is rising. When the switch is off, the diode is conducting for some duration. When the diode is conducting, you are applying minus V naught. Whatever be V naught, you are applying minus V naught, so the current is falling. So what happens when the current hits zero? How do you think the inductor voltage waveform will look like in this condition? And why?
Sir, if inductor current is non-zero, then sorry, zero, and it is not changing, then voltage across inductor should be zero.
Voltage across inductor should be zero. But that you are getting from the current waveform. If I had not shown the current waveform, would you be able to guess that? I mean,
Yes, sir, because diode is also off and
hmm.
switch is also off. So inductor is kind of disconnected. So volt open circuit almost. So voltage should be across it, voltage should be zero.
Okay. So what he is saying is when these two switches are not conducting, if at all there is a state in the circuit where these two switches are not conducting, then you can consider that this point is kind of like, let's say, even if you disconnect this point, it doesn't make a difference because this is completely off. So this point is kind of floating. So what decides the potential at this point? Right? The other end of the inductor is connected to a voltage, and this is open circuit. There is no current. So if you put a multimeter here, you will measure the same voltage because there is no current, there is no drop in this inductor, there is no LDA by dt. And so the voltage at this node should also be with respect to ground, it should also be V naught. So when both the switches are off, at this node there will be V naught because this inductor is open, and this node also there is V naught, so there is no net voltage across the inductor. So you can also identify the stresses seen by the elements, right? So sometimes there could be a confusion that the two switches are off, so I don't know what is the voltage across each. This VDC is kind of getting divided arbitrarily between these two switches. That is also not true. It is not arbitrary. When the inductor is kind of floating, this node voltage will become V naught. So the diode will block V naught, the switch will block VDC minus V naught. You can go back and check. You have done this experiment. You have run the converter in DCM condition. You will see that diode will block V naught and switch will block VDC minus V naught. So we can do the same exercise that we did previously. We can identify the voltage across each element. We can look at the current through each element, but we need to divide it into three states. State one when the switch is conducting, state two when the diode is conducting, and state three when nothing is conducting. That is what we'll do. We'll continue with that analysis. So, uh, so maybe before we go there, we can probably spend a little bit more time on the boundary, and then we will do a detailed analysis of the discontinuous conduction mode. So we'll look at the boundary conduction. So is there something peculiar about this boundary conduction? Can you derive? So for example, I said there could be some arbitrary value of resistance for which this might be happening. Now I'm interested in finding that resistance for a given circuit, let's say parameters, and for a given input voltage and duty ratio. I want to find what this resistance is, at what resistance I can get the boundary conduction. So how would you go about doing that?
Sir, over here, since the waveform is touching the axis, we can say that the average inductor current is half of the ripple.
Correct. So it is obvious, right? These are piecewise linear segments. So the average current should be exactly half of the peak current. So that is very obvious. It's basic geometry. So we can impose that constraint. So you know that your, I mean, average load current. So when I'm representing it with these capital letters, right? That means that I have applied small ripple approximation. So here I have applied small ripple approximation. So this is a fixed value VDC. This is a fixed value V naught. So my output current, the resistor current is constant. It is I naught. And that is the average value of the inductor current. So I can say that the average value of the inductor current is nothing but half of the peak value. So now what is a peak value? How will you find the peak value of the inductor current? Gulshan, can you comment? Hari Krishnan?
So the slope of the graph will be V in minus V naught by L.
Hmm.
So at the maximum point, the slope will be 0.
Here, huh? Why is the slope 0? From the waveform, can you tell me what is the slope at this point?
That will be 0, sir.
Why is it 0? Why do you think the slope is 0?
It is having a change, an abrupt change
So is
into a
the
negative
slope
slope.
defined? Is the slope defined at this point? Is the function differentiable? So this current waveform, is it a differentiable waveform? Is it a differentiable
No,
function?
it's not a differentiable waveform.
Because the slope is abruptly changing, right? So the slope is not defined at this point. So it's not differentiable. It's continuous. But the initial part, your argument is right. So here the slope is, when the switch is on, the slope is VDC minus V naught by L. The slope of this line is VDC minus V naught by L. But at this point, the slope is undefined.
Yes.
So what next? You know the slope of this, but I want to further, I want to find the peak current. So if the slope is VDC minus V naught by L, so what?
Sir,
What
can you
next?
repeat?
Duration is DTS.
Duration is DTS. So it's
You
just the
can,
equation of a line. You can find
yeah.
out the peak current.
Yeah.
So the peak current is nothing but uh, I have found it from the other side. What you have said is also correct. You can say it is VDC minus V naught by L into DTS, or we can say it is V naught by L into 1 minus DTS based on this segment. So both are correct. And the average current is nothing but V naught by R. So do you agree with these two expressions? There is no confusion, right? So if you agree with these expressions, then it is trivial to find the resistance. So you have this constraint, you put in that constraint, and then you know everything else. You know the input voltage, output voltage, inductance, everything, and you can find the resistance. So that is one way to find the critical value of resistance. And typically, this is the condition for DCM. The DCM condition is normally written in this form, which is obtained by solving this expression. So 2L by RTS, this term is referred to as conduction parameter. This term is referred to as a conduction parameter, and you will see this term repeating when you are doing, let's say, this kind of analysis for any converter, let's say boost converter, buck boost converter. You will try to get this 2L by RTS because the circuit parameters L, R, TS, and all is what is affecting the DCM or the boundary condition. That is why we extract out those circuit parameters in this format and call it as the conduction parameter. And if this value is equal to 1 minus D, then you will get boundary condition. If it is less than 1 minus D, then will it be in CCM or DCM? When will it be DCM? When will it be CCM?
Sir, if K is lesser, then it is in DCM because inductance is lesser.
If K is less, then it is DCM, inductance is less. Yes, that is one argument. And again, you can also say in DCM, you can write it based on the average current itself. In boundary, average current is exactly equal to half. When you go to DCM, right, I mean, the average current will become lower than the peak. And when you are in CCM, the average current will become higher than the peak. So if you just put greater than, less than appropriately, you will get. So when 2L by RTS is less than 1 minus D, it will be in DCM. When it is equal to 1 minus D boundary, when it is greater than 1 minus D, it is CCM. This is true for buck converter. You can do a similar analysis for all the other converters that we have discussed. So you will be able to, the expressions are different and the expressions are already derived in Professor Ramnaranan's book. You can refer to that book and try deriving it yourself, because when you look at an expression that doesn't mean anything, the question is, can you derive it from first principles yourself? So at least practice is also important. You try it out. I'm not giving it as a formal homework, but only when you try it out, you will get that speed of analysis, and you will also, you will run into some challenges when you're dealing with other converters. Here it is very straightforward, but again, you just have to remember the four principles that we have discussed. When you are doing this kind of analysis, the first assumption is small ripple. The second is volt-second balance across the inductor. The third is charge balance across the capacitor. The fourth is power balance. So if you invoke these four conditions, you will be able to solve any converter. But but the thing is, it'll become a little bit more complicated than what we are seeing here, and I want you to try it out and figure out yourself. So this is referred to as conduction parameter, and this is the boundary condition. So now we'll actually look at the analysis of discontinuous conduction mode, because continuous we have completed, boundary we have completed. So we'll move on to discontinuous conduction. So again, the thing is, we'll split it into three intervals, right? Three intervals where the switch is conducting, the diode is conducting, no element is conducting, no element, no semiconductor is conducting. So this is the equivalent circuit when the switch is conducting. So when you take the buck converter, I'm just shorting this because the switch is on. I'm shorting this. This is open. So it is just the switch connected to this LCR. So that is what, sorry, the voltage source connected to this LCR. That is what this circuit is. And again, I'm applying small ripple approximation and I'm assuming that I have an ideal source without any, let's say, perturbation or anything. So what is the voltage across the inductor in this state? It is VG minus V. Again, I've slightly modified my notations to match with Professor Ramanarayanan. So far, I was using VDC, but the waveforms and all, he was using this notation VG. So I've shifted it from this slide onwards. But these are very simple things. I don't think it should lead to confusion, and the figures are self-explanatory. So the voltage across the inductor is now VG minus V naught. And so you are applying a constant voltage VG minus V naught. The current is going to increase. And we know it was in discontinuous conduction, the inductor current was 0 before we turn on the switch. That is why we are starting from 0. We don't have to worry about the initial condition because we know that the initial inductor current is 0. So that helps us draw the inductor current waveform in this duration. And then what is going to happen in this duration? Manoj Yadav, can comment. What is going to happen in this duration?
Hello, sir. In this condition, I think inductor will charge negatively, and it.
So will the current continue to increase?
Yes.
Huh?
In inductor. In inductor, yes, sir.
What is the polarity of the voltage that you are applying here? What is the voltage across the inductor in this state?
Exactly, sir. Plus minus.
No, here the voltage is VG minus V naught. Here, what is the voltage? What is the voltage across the inductor in this state?
VG minus V naught.
In this circuit, look at this circuit. Is there VG?
Okay,
so
okay.
This.
Got it.
In this circuit, what is the voltage that you are applying?
V naught.
Plus V naught or minus V naught?
Minus V naught.
So what will happen to the inductor current? You've just seen the waveform, right? In the previous slide, I mean, 2 slides before I showed you. So do you understand what this circuit is? What is this circuit?
Yes.
This is the circuit when the diode is conducting. So this is the state 1. When the switch is conducting, this is from 0 to DTS, right? So 0 to DTS, the switch is conducting. So you are applying VG minus V naught across the inductor. So at DTS, the switch is turned off. So the diode comes into conduction. So that is why this is shown as a short circuit and this is an open circuit. So I have not shown this part of the circuitry. So I'm only showing this LCR shorted through the diode. So that is this circuit, right? So this is the second state where the diode is conducting. So when the diode is conducting, now you have said you are applying minus V naught across the inductor. So at this point, till here from 0 to DTS, this was your circuit. At DTS, your circuit changes to this because the diode comes into conduction. Now what happens to the inductor current? Manoj, I want you to answer. I will not proceed unless you answer.
Inductor current will discharge.
Inductor current should decrease because you are applying a negative voltage across the inductor. The current should decrease. With what will be the slope of the inductor current? Here you tell me, in this circuit, what is the slope of this current? Again, we discussed this just a bit earlier. What is the slope of this current? This segment.
Mm.
You have a pen and paper with you.
Yes, sir.
You write the voltage equation across the inductor. What is voltage across the inductor? What is the expression? General, if you have an inductor and if there's a current through it, what is the voltage across the inductor?
LDI, LDI by dt, sir.
So
And
what did I ask? I asked you for the slope. The slope is what? Di.
yes,
So what di by dt? What is the slope? Di by dt. What is the slope di by dt?
yes, sir. So VL by L.
VL
Inductor
by L. So here what is VL? In this state, what is VL?
minus V naught.
In that is true here. In the first state, it is Vg minus V naught by L. In the second state, it is going to fall with the slope minus V naught by L.
Yes, sir. When the discharging minus V naught by L.
So these things are, I mean, very, very fundamental, and you should be very quick at this. Okay. So this just shows a lack of practice. So you just practice it. The basic topologies and all the waveforms that I drew in class, you try it for all the three topologies, buck boost, buck boost. You should be, even if I call you in your sleep, you should be able to draw these waveforms. If you reach that level of comfort, then only things are good. So try practicing, because these are simple things. Once you understand the fundamentals, it will be very easy, but it takes a little bit of practice also. So try practicing the waveforms for buck boost, take CCM. At least you should be able to draw from first principles, and make sure that you are very comfortable. Okay.
Okay.
Yeah. So in the second duration, the current is going to fall, and we are going to apply minus V naught. So this point in time, I am calling it as D2TS. So this is a new notation that is being introduced. So the diode is conducting between DTS and D2TS. So what is the third circuitry? When both the switch and the diode are not conducting, so this will become open, right? So it is just an LCR. So the third circuitry is just an LCR. And this is true from D to TS to TS. So from D to TS to TS, there is no current in the inductor. So the current stays at 0. And there is also no voltage across the inductor. So the voltage also stays at 0. So this is the voltage waveform across the inductor, and this is the current through the inductor in discontinuous conduction mode. And then the cycle just repeats. And the peak value is IP, the average value is I naught. I'm using the same notation. So peak value is IP and the average value is I naught. So now that we have understood the shape of the waveform and we have an understanding of the voltage across the inductor, the question is, can we derive the voltage gain of the converter under DCN? Because previously the voltage gain was independent of the load. In continuous conduction mode, when you derived, you saw that the voltage gain was independent of the load. Now we will see that it is not that easy or simple. It is going to be dependent on the load. And now our challenge is to break that. I mean, to find an expression for the voltage gain. So again, the concept is same. You apply volt-second balance on the inductor. Right? So you take the inductor and you divide it into 3 intervals and you apply volt-second balance. So if you apply volt-second balance, in the first interval, you are applying Vg minus V naught into DTS. In the second interval, you are applying minus V naught into, yeah, I think there's a mistake in this expression. It should be D2 minus D into TS. Okay, it should be the second interval duration. So based on the definition of D2, I think there's a mismatch between my diagram and the expression. So I apologize for that, but you correct it appropriately. So if this duration, if we call it as D2TS, then it will be rectified. Maybe I'll correct it dynamically on the fly. I think this is an image, I can't correct it. But the thing is, this duration is D2TS and not this point. Okay. So otherwise, what I've shown is incorrect. If this duration is D2TS, this duration is DTS, the second duration is D2TS, then I can write this expression. That is, in the first interval, I am applying Vg minus V naught into DTS. The second interval, I am applying minus V naught for this duration. So either it is d2ts if you consider that it is this duration. If you follow the notations in the diagram, it will be d2 minus d into ts. But anyway, you guys are smart, you understand that. But there is a mismatch, there's a mistake here. So I want you, if you're taking notes, you correct it in your notes. So if we assume that
Sir,
this
sir, can I say something?
Go
Sir,
ahead.
according to the image you have shown, the output voltage becomes D by D2 into Vg. So if we put D2 equals to 1, it's again the main expression we use for CCM. So it is self-explanatory. It is more easy to understand.
So you prefer the notation that I'm using.
Yes, sir.
Yeah, which I'll suggest you to go with whatever you are comfortable with. But now we are only interested in how to analyze this. So the idea is apply volt second. Whichever notation you use, you apply volt seconds across the inductor. That is the voltage that you're applying in this duration multiplied by the duration, Vg minus V naught into dTs. Second is the voltage that you're applying in this duration multiplied by the duration. So whatever be your convention. So you stick to your convention, but make sure that you are consistent and don't make mistakes like what I did. And then the third duration, there is zero voltage, and whatever be the duration, it doesn't matter. There are no volt seconds here. So this area should be equal to this area. There should not be an average voltage. That's all. So if you impose that constraint, you will get a relation between V naught and Vg as a function of d and d2, as a function of these two durations. So that is clear. Is it clear to the class? At least one or two of you can respond. You understand what we are doing?
Yes, sir.
So the thing is, we can say that D is like a control variable, right? So we are applying a
Sir,
uh,
sir, in message in chat, Vandana has written that she is feeling the class is going little fast.
okay. So Vandana, what part do you feel is fast?
D2 TS to TS.
The previous slide, huh?
This slide, sir.
No, this slide we haven't reached there. Okay, fine. So you stop me, okay? Don't write in the chat window. I'm not looking at the chat. So you just unmute and say, don't worry about interrupting the class. If you feel that I'm going fast, you just interrupt me and say to slow down. Okay.
Yes.
Yeah. So in the first interval, what is the voltage across the inductor? You tell me, Vandana, you tell. What is the voltage across the inductor?
VDC minus V naught.
VDC minus V naught. Or in this diagram, VG minus V naught. In the second interval, it is minus V naught.
Yes.
In the third interval, what is the voltage? In the third interval,
right side of inductor it is V naught, but left side I didn't understand how V naught came, sir.
It's an open circuit, right? Is there a current through this inductor?
Oh, sir.
So
that means potential is
the potential should be same. So if you put a multimeter here and measure, you will measure the same V naught. If you take this circuit, let's say somehow you charge the capacitor to some voltage, and then if you put a multimeter here, you will measure the same voltage.
Yes, sir.
So
understood.
So this voltage is zero. So there is no volt seconds that gets added up in this interval. So it is only the first two intervals that you have. So you are applying a positive volt second in the first interval, you are applying a negative volt seconds in the next interval, and these two areas should be equal. So which is same as what we analyzed in CC.
Yes.
That is what I've written here, but again, just be consistent in terms of expressions. Okay. You also understood the mistake that I was pointing out, right? Vandana, did you?
It is D2 minus D.
So either there should be D2 minus D according to this diagram. Or else, if you consider this interval as D2TS, then this expression is correct.
Yes.
The expression is, the issue was that I was taking some pictures from Professor Ramanarayan's book and the derivations, and in the book, probably I added some of these on my own, and I was doing it in the middle of the night, so I made a mistake. But the thing is, this duration, if you consider it as D2TS, then this expression is correct.
Yes.
So That's all. But anyway, you know how to analyze it. And then you get a relation between output voltage and the input voltage. And as a function of these two durations, the first duration or the duty ratio and this, let's say this D2, you get an expression. Whichever way you define it, you will get a relation between V0 and Vg as a function of D and D2. And now the problem is there are too many unknowns. We don't know what D2 is. We know D because that is something which is in our control. We know the duty ratio. We are fixing when the switch should conduct. But how long the diode is conducting is not in our control. It is purely decided by the circuit parameters, L, C, R, and switching frequency. So it is dependent on mainly L, R, and switching frequency. So D2, the duration D2 depends on the circuit parameters. And now the question is, we have to eliminate this, right? Now you have one equation and there are, let's say, multiple unknowns. You don't know V0, you don't know D2, right? So the objective is, can we find V0 or can we find the output voltage or the gain under this condition? And again, there is an unknown. So we have to break this problem. So we need one more relationship between D and D2. So can we find that relationship by looking at the current waveform? Right? Can we again, just like in the boundary condition or boundary conduction mode, you derive certain relationship between the peak current and the average current. Here, can we find out a relationship or can we try to look at the peak current and the average current expressions? So that is because we need one more condition and we only have these two waveforms. So we can try to get as much as detail as possible from these waveforms. So now again, what is the expression for IP? You can either consider this interval or this interval. So here, I think I have considered this interval, again, assuming that this duration is D2TS. This duration is D2TS. Maybe, I'll correct it explicitly. So if you're comfortable with the older notation, you can derive it appropriately. Here I'm just correcting the mistake. Yeah, so now at least the expression should be consistent. So this duration is DTS, this duration is D2TS. And then you find the first relationship. To find the second relationship, we are trying to, let's say, see whether we can get any more information from the current waveform. Can we relate D and D2 using the average current and the peak current expressions? So what is the peak current? You can take either of these intervals, right? So if you take the first interval, we know it is Vg minus V0, let's say by L into DTS. If you take the second interval, it is again minus V0 by L into D2TS. So that is what I have written. And I'm only interested in the peak current. That is why I dropped the sign. So it is in this interval, the voltage that is applied, the magnitude of the voltage is V0 and the duration is D2TS. So V0 into D2TS by L is the peak current. And the average current is nothing but V0 by R. Right? Yeah, I mean the average current in the inductor, it still holds good because charge balance in the capacitor has to be there. So the average current in the inductor is nothing but V0 by R. So this I0 is V0 by R. And what is the average current? Can you find the average current from this waveform? So can one of you tell me, maybe Siddhartha, how would you find the average current from this waveform?
The area under the triangular waveform, ITS.
Yeah. So the area under the triangular waveform. So the area under the triangle is half into base into height, right? So the base is.
So I have a question.
Yes.
In D2TS to TS, when no switch is conducting, The capacitor will supply the load current.
Correct.
Oh, okay.
Correct. It's correct. So here you can just take the average value of this waveform that you are familiar with. Find the area under the curve, and the area under the curve is half into base into height. Right? So you can do that, and you will get the average current. And then using these two relationships, you can relate d and d2. You get another expression for d and d2 using this. So you substitute this peak current expression in this, and you get a relationship between d and d2. And again, here you will see the conduction parameter coming again. And this is true for buck converter. You can find a similar relationship for boost converter, buck boost converter, and all. So now you have two expressions, and using that you can solve. You can now find d2. You can now find v0. I have not done that last part. I leave that as an exercise to you. So you can compute, the objective is to compute the voltage gain expression, and we have done that. We have done that in terms of d and d2, and then you have one more equation that relates d and d2 with the circuit parameters. These are all known parameters. So now you have two equations, you have two unknowns. One unknown is v0, one unknown is d2. You can solve this to find the let's say voltage, or you can do this to find the voltage gain or the output voltage under DCM condition. And this is the procedure that you can follow for any converter, whether it be boost converter, buck boost converter, any Chuk converter. This is the procedure that you can follow. Apply volt second balance to find the voltage gain, but again, because you will have an extra unknown in the case of discontinuous conduction mode, so you have to find one more constraint based on the current waveform. So you can derive it in many different ways. I'm just showing one way based on Professor Ramanathan textbook derivation, but there are other ways in which you can get the second constraint. So now, is this clear? Any questions? Vandana, do you understand the points?
Sir, we have to find voltage gain in terms of D in DCM also, sir, here.
Yeah, which is what we have done. But the only thing is, previously it was just D, right? If you just take a buck converter, it was just D in continuous conduction mode. So now it is not D, it is D by D plus D2. So there is this D2 also coming in. So unless you solve for D2, you cannot find the voltage gain. So let's say I want to find for a given value of R, L, C, and things like that, I want to find what my voltage gain would be. But now I am unable to do that because D2 is unknown to me.
Yes.
That is why we are looking at the second constraint. So if you know D, you know L, you know R, you know TS, from this equation you can find D2. It's a quadratic equation. You can solve this and you can find D2. So one root will be a realistic value, one root will be an unrealistic value. You may get a negative number or whatever. So you can find D2. And once you find D2, you can find your voltage gain.
Sir, that means there in CCM, voltage gain is not dependent on the elements, but in DCM we get a
load dependent expression. The DCM voltage gain is load dependent. So as you change your resistance, if you are in DCM, your voltage will keep on changing. Yes. That is the implication. Yes. The voltage, output voltage is no longer constant. In CCM, as long as the conduction was continuous, and if you are looking at an ideal converter, your output voltage will remain constant. It will only depend on the duty ratio and the input voltage. But the moment you enter into discontinuous conduction, the load resistance plays a part. So if you change the load resistance and the converter is in DCM, the output voltage will change based on the load resistance.
Sir, then is it undesirable to make the converter work in DCM, or?
It is not. It has advantages and disadvantages. For example, by looking at the slide, can you tell me some advantages or disadvantages of DCM? Can you guys think? I mean, I'm not just asking to Vandana, I'm just asking to the entire class. So what do you think could be the advantages? What do you think could be the disadvantages?
There one disadvantage could be in case of DC motor load type of things, because torque will then will be discontinuous if inductor current is discontinuous.
Yeah, but you also have a capacitor. We are assuming that the load current is still constant, right? I'm still assuming small ripple approximation. The load current is a constant current. The ripple is absorbed by the capacitor.
Sir, maybe conduction loss get reduced because both switches are not conducting for some time.
That is one thought. Hold that thought. That may be true, may not be true. But so
Sir,
Vandana's argument is that both the switches are not conducting for some time, so the conduction loss should be lower. I want a class to respond, or maybe if you have a different perspective, bring that to the
sir,
table.
one advantage which I guess is that the output voltage will be increased since the average area is positive, little more positive.
Yeah, which is what you saw in your diode rectifier also, right? In your diode rectifier also, we saw continuous conduction and discontinuous conduction. And in discontinuous conduction, you always saw that the average output voltage was slightly higher than the continuous conduction. Here also it is true. The average output voltage will be, it can be higher. So you can get a, but in continuous conduction, you can get that higher voltage by increasing your duty ratio. So it is only for the same duty ratio, you are right. Your average voltage will be higher. But that as such, I cannot say it as an advantage because I could have operated it at a different duty ratio to get a higher voltage. You understand my argument?
Yes, sir. Yes.
Sir, in DCM, the inductance can be reduced, so I guess the size might come down of the inductor compared to, let's say, CC.
So what determines the size of the inductor? You remember your inductor design experiment. How what are all there in the inductor sizing? Any of you, can you remember the
Core material?
Yeah,
So
don't get into that.
the RMS current and the peak current plays a great part in AC and AW
It
selection.
also plays a part, right? So if you remember, the size of the inductor is proportional to L into I peak into I RMS. The area product is proportional to. What can you comment about peak current and RMS current? Because you are only looking at the inductance. That I mean, one part of the argument is correct. That is, the inductance value could potentially be lower, because that is one way for the same loading condition. The way to operate your converter in DCM is by choosing a lower inductance. Yes, the inductance may be lower, but we also have to look at peak and RMS current before commenting on the size. So let's say I want to send the same, because when we are comparing, there has to be some fairness, right? So I'm saying that my output voltage is same, my load resistance is same. In one scenario, a buck converter is operating in CCM. In one scenario, it is operating in DCM. These are, let's say I have two buck converters. Let's say one converter Sambit has designed, one converter Vandana has designed. And Sambit has designed to operate the converter in CCM. Vandana has designed to operate the converter in DCM. And they are feeding the same load. The output voltage is also same. So the implication is that the circuit parameters could be different. They may be operating at different duty ratios, but they are getting the same output voltage. So under these conditions, we have to make a comparison. So for the same load current, what can you comment about the inductor current waveform in CCM and DCM? The average current is same. That is the assumption that I'm bringing in. I have two converters. The average current is same in both the converters. But between CCM and DCM, what can you comment about the current waveform?
Sir, the
Sir, if the average current is same, then
higher.
Yeah, one at a time. So I think Deependu was talking. Who was the other person?
Arun, sir.
Arun. So maybe Arun, you go ahead first, and then we'll hear out what Deependu has to say.
So for the same average current in the inductor, in case of DCM, the ripple should be higher.
The ripple should be higher. Deependu, what was your point?
Yes, sir. I was also going to say the same thing.
Same thing,
Means
right?
the peak current will be higher.
Peak current will be higher. Peak current will be higher. So you cannot easily comment on the inductor size. You have to do some due diligence and you have to check. So that is a caution. Just because the inductance is reducing doesn't mean that the size will always reduce. It could reduce. That's all I'm saying. But you have to look at the peak current. But the point is that the peak current is significantly higher in DCM compared to CCM. So you have to rate your devices and all to carry that peak current. So that is one. So whether you decide to operate in CCM or DCM may have an implication on the selection of devices. And the discontinuous conduction mode will have higher ripple. And then the capacitor will also see that higher ripple. And you have RMS again, you have to compare which one will be higher, whether it will be higher in CCM or DCM. At least you can take an example condition, and then you can have two different designs, one in CCM, DCM, and you can compare. So that way you will get a quantitative number. Expressions are anyway given in Professor Ramanarayan's book or Erickson's book. So you can do it, I mean, comparison and get a feel for yourself. But it is prima facie, it is not very easy to say whether one is better than the other. Later on, when we go to controls and all, there are certain advantages to operating in DCM. We'll probably not cover that in the basic power electronics course, but you will definitely learn that in SMPC, especially when you do, let's say, different types of controls, when you're doing voltage mode control, when you're deriving the transfer functions, right? You have now, all of you have derived the small signal transfer functions for CCN, but you could, if you're interested, right? I mean, at least I will recommend the PhD students to do so. MTech students, I strongly recommend, but again, you are taking 5 courses and many of you are already complaining that you are not able to meet the workload, but I strongly recommend that you try it out. Extend that small signal analysis to DCM and look at the transfer function, or at least look at the textbooks and see the derived transfer functions. If you are not deriving it yourself, at least see the transfer functions and see if there's a difference. So when you're comparing, you should actually holistically look at the converter operation under different conditions. So we are looking at the last signal analysis because that is what we have studied. We are looking at the waveforms and we are trying to see what happens to the ripple, what happens to the stresses and the components and things like that. The second thing is, from the perspective of control, is there a difference? I mean, are the transfer functions going to be same? Are they going to be different? If it is different, is there any advantage or so? So I leave it at that. I want the students to explore it a bit, but definitely when you're operating it in DCM, there are certain advantages when it comes to control. And what that advantage is, maybe think about it. And if you guys come back, we'll probably have a brief discussion in the class, but I want you guys also to put in some effort. So it is, so again, coming back to original question asked by Vandana, it is not a disadvantage to operate in DCM. Sometimes it is desirable to operate in DCM because both features offer certain unique, let's say, operating advantages. CCM, I mean, the advantage that you get is it is load independent. But DCM, it is load dependent. The voltage becomes load dependent, but again, you may get some other operational benefits. So we have looked at the derivation of the voltage gain. Now the next part is, I'll move on at this point, unless you have any other questions. Any questions?
Sir, from the voltage gain expression in DCM, for a fixed duty ratio and input voltage, we can see that output voltage is lesser than as compared to CCM mode.
Why do you say it is lesser?
So V0 by Vg is d upon d plus d2. If we are fixing d and Vg to be the same as in CCM modes and d2 is coming extra in denominator.
No. In CCM, what was this expression? It was only d, right? In CCM, V0 by Vg was d.
Yes.
So now it is d upon d plus d2. Is d plus d2 greater than 1 or less than 1?
So like d is 0.5.
So look at the waveform. So whatever be d, let's say d is 0.5, but what about d plus d2? Is it greater than 1 or less than 1?
Less than 1, let's say 0.7.
If it is less than 1, is this expression higher or lower?
So 0.5 by 0.7. Yes.
It is higher than 0.5, right?
Yes. Okay.
Yeah. So the expression, the voltage will be higher in DC.
Yes.
Any other comments? Any other observations, points? Yeah. If not, we'll move on. We'll move on to the current and voltage ripple. Again, I have made the same.
Sir, if peak current is higher in inductor in DCM, then rating of switches will be different. And also, if V naught is higher for a fixed DT, I'm talking about, then we need the voltage rating of diodes and all. We have to be increased. That is a disadvantage.
Correct. But again, for the condition that I was pointing out, so see the voltage rating of the diode, it is a bit tricky. It depends on the fairness of the comparison that you are making. So I said that my load requirements are same between CCM and DCM case. That is, my output voltage is not changing. My, let's say, the only thing is one of
In
you is
that case, only
deciding.
current will be different.
Only current will be different. So it depends on the fairness of the comparison, right? So it depends on the fairness of the comparison. If the output voltage is held constant, the voltage rating will not change. But if you take one converter in CCM, DCM with the same load, but if you operate it at the same duty ratio, I agree with you. The output voltage of DCM converter will be higher than the CCM converter. So the diode will see a higher stress. But when we are selecting the switches, we select that based on the application of the input and output voltage constraints, voltage and the power constraints. Right. So there we cannot generalize and we cannot make a statement that the voltage ratings will be higher in DCM. So it is defined by the application. Do you agree?
Yes, I understood.
Yeah. So we'll move on. We'll move on to the ripple. So now, yeah, I had made the same mistake. I've corrected that. So these are the three modes, right? When the switch is on, when the diode is on, when the both the switch and diode are off, and we have seen the waveform. And now, uh, how about the current and voltage ripple? The current ripple, as we have, it's straightforward. You have the waveform. You can find the peak current, which we have already found, and the peak current is nothing but the peak-to-peak ripple. So it is D2 TS V naught by L. And again, we have found out the average current. It is nothing but the area under the curve. So we have already found the current ripple. So how do you find the voltage ripple? What did we do for CCM? How did we find the voltage ripple for continuous conduction mode?
The area under that IC.
IC. So first is we have to look at the capacitor current. And how will capacitor current look like in this case?
It looks same as IL with the DC shift went down.
Sir, in case of DC,
In case of DCM, in this case.
Okay. So the waveform till the region of where any diode or switch is conducting this waveform without the DC offset, and in the discontinuous mode, it has to supply that average current out. So that would be a constant I naught.
We are talking about the capacitor current. So you are saying that okay, when none of the switches are conducting, the capacitor will feed the I naught. That is what you are saying.
Yes, sir.
Yeah. So when the switches are not conducting, this capacitor is feeding the load current. That is correct. And when the switches are conducting, yes, but again the thing is we can apply charge balance in the capacitor, and we can assume that the average current in the capacitor is zero if the circuit is in steady state. The average current in the capacitor is zero, then I can just let's say, and the other assumption is that the load current, I'm applying a small ripple approximation at the output. So that means my load voltage is steady. There is no ripple in the load voltage. That is the assumption. So assuming that the current in the resistor is kind of like DC, it is nothing but the average current of this inductor. So then all the ripple should be flowing in the capacitor. That is again an assumption that we made in CCM. Here also we are going to do that. So like I think Siddhartha or somebody who pointed it out, this waveform is just going to get DC shifted. Right? So the capacitor current is going to look exactly like that. It is getting DC shifted by I naught. So the peak is now going to be IP minus I naught, and this valley is going to be minus I naught. So this is clear. Vandana, is this clear to you?
Yes, sir.
Manoj Yadav, is this clear?
Yes, sir.
So anybody, if you have any doubts, confusion, please stop me and please ask. Okay, if you think I'm going fast or something, please stop me. So this is how the capacitor current waveform is. Now what? What next? We have gotten the capacitor current, but I am interested in finding the voltage ripple. What is the next step?
So we have to
One by
find the
three.
area.
Which area?
So either the positive or the negative both should be same.
Yeah, either this area or this area. Again, there is charge balance, so these areas should be same. So you can find out any one of those areas, right? So here I'm shading the positive area, and you have to find this area. But what is the challenge in finding this area? You know the peak, IP minus I naught, but this duration you have to find it. It is not difficult. But you know the starting point. You know that the starting current is minus I naught, and you know the ending current is IP minus I naught. You know this duration, so you can write the equation of the line and figure out when it crosses zero. So that will give you T1. Likewise, here you know IP minus I naught. Here you know minus I naught. You know this duration is D2 TS, and in the previous slide we have seen how to solve for D2, right? So D2 everything is known to you. So again you solve this lines equation, figure out when it is crossing zero. So you find T1 and T2. If you find T1 and T2, you can find the area, right? It is half into base into height. But then you will get the charge, and from the charge, Q is equal to C delta V. You can find out the ripple voltage. And again, here, what will be the nature of the ripple voltage? Or I don't have a writing pad or anything. I'll try to draw with the mouse, but the shape will not be accurate. So, but let's try to see. Again, where do you think the ripple is going to have its peak, the voltage ripple? Where do you think it is going to have its minimum? Again, based on the same analysis that we have seen in the CCM operation of the buck converter. So if you take this, right, in this interval, you're always injecting a positive current into the capacitor. The nature may be increasing, decreasing, but it doesn't matter. The current is always positive. That means the capacitor voltage will keep on increasing in this duration. And here in this duration, you are injecting a negative current, or you are taking out some negative current. So in this duration, the capacitor voltage will keep on decreasing. So we know that this is the point where we should see a maxima. This is the point where we should see a minima. And the nature is going to be parabolic, let's say, because it's a ramp. So the nature is going to be parabolic in this region. And here again, this parabola will continue. Here the current is constant, so it should fall linearly, right? The current is constant, so you are drawing a constant current from a capacitor. So the capacitor voltage should fall linearly. So here the shape will be linear, and again after this it will become parabolic. So pardon my drawing, but yeah. So again, if I assume that here it should reach to the same condition. Try to. It will be something like this. In this region, it is going to be a straight line. In all the other regions, it will be parabolic. But you can draw the shape, and that may or may not be there in the textbook. I'm not sure, but you can try drawing it yourself, and based on the current waveform, and you can maybe try simulating it and kind of cross-validate whether what you have drawn is correct or not. But I recommend you to do this mental exercise. The more you do it, the better you get. You should try solving for this waveform, because all these waveforms, whether it is CCM, DCM, you should be able to draw, and you should be able to draw that very quickly. And that is the level where I want you to be, so that you are ready for your other courses and even ready for your projects and all in power electronics. So at least this analysis, you should be very strong. And especially visualizing the waveforms. I don't want you to remember any expression. You can derive all the expressions from scratch, but I want you to be able to draw all the waveforms from first principles. That is if not anything, that is the only one thing that I want you to learn from this part. You should be very clear in analyzing or looking at the waveforms, and by waveforms I mean every waveform, every voltage and current in every element in the converter. So you should be able to derive that. And till you reach that level of comfort, you need practice. So there are several practice problems in the textbooks, in Professor Ramnaran's textbook, in Erickson's textbook. So you try doing the practice problems, or you try, let's say, deriving things yourself, at least for the basic converters. So only repetition will give you that practice. So we are discussing for buck, but you should do it for boost, buck boost and all at least. And if possible for Chook also. Chook is very interesting. I mean, there are two inductors, and the definition of continuous, discontinuous, it can become very interesting. At least I want some of you to think about it. I mean, if you can do that for the Chook converter, that'll also be good. But I'll leave that exercise to you, because I can only teach you so much. Finally, it is your effort that is going to pay off. So spend some time in analyzing, applying whatever you have learned to all the other converter topologies. So any further points on this slide? If not, we'll move on.
Sir, can you please explain how to find D1 and D2?
D and D2. So we have discussed that here. Yeah, this slide. So you need one more constraint. D is something that you know. Let's say you are fixing the duty ratio. So D, we'll assume that it's a known quantity. The unknown quantity is D2. So you have to find the relationship between D and D2 using the circuit parameters, and you can use the current waveform to arrive at that. So you can find the expression for peak current, you can find the expression for average current, and then using these expressions, you will get a constraint. So this is, if you use these two expressions, you will get a quadratic equation in D2. Right? You will get a quadratic equation in D2, and by solving this, you can get the value of D2. This is for buck converter. For boost and buck boost, the idea is similar, but you have to use a current waveform to find the expression for D2, but the steps may be slightly different. That's why I want you to try it out. Is it clear how to find D2?
Yes,
sir, I think, sir, can you explain how to find the time zero crossing time T2 for the capacitor current?
So let's say you have found D, D2 and R. So you know everything. You know the duty ratios, you know DTS, you know D2TS, and then it's just the equation of a line, right? I mean, you know the peak value, IP minus I naught. You know the expression for IP, you know the expression for I naught, you know, and the value is minus I naught. You know the starting point, you know the ending point, you know the slope. You can write the equation of this line, and this line crosses zero, right? So you solve for that point. That gives you T2. The intersection of these two lines, right? So you write the equation of this line. This is the x-axis. So find the intersection of the lines. That's all.
Then won't the minimum voltage of capacitor be at 0 instead of D1?
Why do you think the minimum will be at 0? So after this, what are you doing? Here, what is the current in the capacitor? In this region?
It is increasing from minus I.
It is increasing, but what is the polarity? Is it positive or negative?
Negative.
It is increasing, but it is still negative. So you are still taking out the capacitor. Current is, let's say it is, let's define, let's say I'm defining the polarity of the capacitor like this. And let's say I'm defining the current like this. So now it's a negative current. The current is going out. So you're continuing to discharge. The rate of that discharge is slowing down because it's an increasing current, but the current is still negative. So the capacitor is still getting discharged. So while the capacitor is still getting discharged, how can the minimum come here? Right? The minimum should come here, because only after this point the direction of the current reverses and the capacitor starts charging again. So this is the point where you should expect the minimum voltage in the capacitor.
Yes.
Okay, good. So that's all. I mean, that is all I wanted to discuss about the steady state analysis. So now you know how to analyze the continuous conduction mode operation. You know why it is called as continuous conduction and discontinuous conduction. It is not with respect to the current waveform. That is, this waveform is still continuous, but it is with respect to the conduction of the semiconductors. There exists a duration where none of the semiconductors are conducting. That is why it is called as discontinuous conduction. And then we have looked at, let's say, how to analyze or how to derive the boundary condition. That is, we found the relationship between the peak current and the average current. And this is a concept that is going to help you, especially in boundary and discontinuous conduction analysis. You draw the current waveform, find the expression between the peak, find the relation between peak and average. So by solving that relation between peak and average, you are able to derive the conduction parameter K. So the conduction parameter K can be used to understand whether the converter is going to go into CCM, DCM, all that. So that's what we did in boundary conduction. And after that, we looked at proper discontinuous conduction. So when you go into discontinuous conduction, there are three states: when the switch is on, when the diode is on, and when no semiconductors are conducting. So for each state, we can find the voltage across the inductor and the current through the inductor, and then we apply the same set of steps what we have used in CCM. We apply volt second balance across the inductor. You get an expression for the gain in terms of D and D2. But previously, volt second balance alone was sufficient. When the converter is operating in CCM, volt second balance across the inductor alone was sufficient to derive the gain of the converter. But the moment you go to DCM, that alone is not sufficient, because now the gain is also dependent on the load. So volt second balance across the inductor gives you one expression, but there is one unknown. The output voltage is an unknown, and the duty ratio D2 is also an unknown. So since there are two unknowns, you need one more constraint. So that is where the current waveform comes in. Find the expression or relationship between the peak and the average value of the current, and that will give you another constraint. And using these two constraints, you can find the gain of the converter. And using this, you can find the output voltage D2 and everything. And then the only part that is remaining is the ripple, the current and voltage ripple. Current ripple, again, it is straightforward. From the current waveform, you can derive. For the voltage ripple, procedure is identical. You draw the capacitor current waveform. So assume that all the ripple flows into the capacitor, and that all the DC flows into the load. Then you draw the capacitor current waveform. Then you find the charge enclosed, and that will give you a way to solve for the ripple. That's pretty much it. So the analysis, the procedure is same. Doesn't matter whether it is CCM, DCM. If you understand the fundamentals, only those four things that I said: small ripple approximation, volt second balance, charge balance, power balance. If you apply these four principles, you can solve any converter, any basic converter. And for analyzing that buck converter, we never invoked power balance. It was not necessary. But when you are solving for boost converter, buck boost converter, and all, power balance will also be needed. But I want you to try doing that by yourself. Yeah. Now we'll move on to the DC-DC converter dynamics. Again, we have had some discussions. We have said, why do we need feedback control and all? Because we had some discussions when you were doing your experiment. So we have already established the need for feedback control, because there could be variations. The input voltage could vary, the load could vary, right? I mean, under all these conditions, you want to regulate your output in the presence of, let's say, disturbances, in the presence of line variations, load variations. So all that you cannot achieve by open loop. In open loop, let's say if the objective was only to do reference tracking, that is, we want to track a reference. I want to say that my output voltage should always be at 10 volts. That is the objective. So if I perfectly know my plant, then I can just be in open loop. I can invert my plant. I don't need a controller. I can invert my plant and I can still get the same output. But in reality, there are several uncertainties, because your plant, now that you have derived the transfer functions, you will see that your plant transfer function is dependent on the circuit parameters. So when the resistance changes, actually the plant transfer function is changing. So when there are plant variations and all, you cannot always compensate for the plant because you don't know what the load is, right? I mean, the load may be changing based on the application, so you cannot always predict. So you cannot always predict and mitigate for the variations in the transfer function. So when there are uncertainties in the system, we need feedback control to handle that. So we'll discuss this in a bit more detail when we start the controller design. So at least we have established that there are uncertainties in our system and there could be variations in the line parameters, load parameters and all. And because of which we need to implement the feedback control. That is something that we take for a given at this point. And again, I'll repeat this when we start the control discussion. So now let's go ahead with the fact that, okay, we need a controller. So how do we design a controller? So designing a controller, I mean, is several steps away. Before even designing the controller, we have to understand the system that we are trying to control. Here we are trying to control a buck converter. We need a model for the buck converter suited for controller design. Right? Again, we have seen that this converter is not like any of the other systems that you have seen. So previously, let's say in your BTech and all, you have studied about LR circuits and things like that. They are all linear systems, right? If you give a fixed frequency input, you get, let's say, the output will also be of the same frequency. There could only be a phase shift, but at least they followed the principles of linearity, superposition. They were linear systems. But the buck converter is a non-linear system. And why it is a non-linear system, again, it will become apparent. So we have a non-linear system at hand, and all we know so far are linear system theory principles. I don't know if any of you have studied nonlinear control and all, but at least anyway, for the context of this course, we will not go into complicated nonlinear control approaches and all. We will stick to the fact that we know control design based on linear system theory. So if we have a linear plant, if we have a linear system, then we have several techniques. You are learning time domain techniques in Professor Jayan's class. You are learning how to design controllers by, let's say, placing the poles and zeros using root locus. That is one. So that is a time domain technique to design controller. Then in BTech, you would have definitely used Bode plots, Nyquist plots and all. So those are frequency domain techniques. You can use these Bode plots and all to analyze transfer functions. And then you can also use those tools to design your controller. So there are time domain techniques, there are frequency domain techniques that can be used, provided your system is linear. So now our system is non-linear. So the best we can do is around an operating point, can we linearize the system? And then can we, for that small, that is the small signal modeling. That is what is referred to as small signal modeling. The objective is our system is non-linear, highly non-linear. But we only know linear system theory principles, or we want to make use of the tools to design control systems, or we want to use those tools to get insights about the converter operation. So for that, we have to linearize the system around an operating point. So in a small operating regime, we can consider that the converter is like a linear system. So in that regime, we can use these tools and techniques that we have studied to analyze the converter, to design the controller and all. So the question is, how do we linearize the system and how do we do a model? The objective is to come up with a model. The objective is to get a transfer function for this buck converter so that you can use it to design a controller, or you can use it to study the dynamics of the system. That is kind of like a high level motivation. But all these points we'll go into deeper details in class. So how do we analyze? Right now, we'll just discuss a procedure for analyzing this converter. Right? So again, we can break this into, right now we are sticking to CCM. We are not going to DCM. So if it is CCM, we have two states. We have an on state and an off state. If it is DCM, we'll have three states. But the procedure that I'm discussing will also hold good for DCM. But right now, for simplicity, we'll stick to CCM. So you divide the circuit into two states, the on state and the off state. And now we have removed the switching elements, right? I mean, in the on state, it's just a linear circuit. In the off state, it's again another linear circuit. So can we find, let's say, can we derive the fundamental relationships? Can you write the governing equations for the circuit when it is in on state? That means when the switch is on, can you write the governing equation for the circuit when the switch is off separately? So, and again, these governing equations, right? I mean, it could be, you can write a differential equation, but so that is one part of it. The second part is there a systematic way in which we can write these system of equations, right? So again, there are different principles. Erickson will talk about a certain way to do things, and Professor Ramanarayanan's book will talk about a slightly different way to do it. I'm okay. If you follow any method, I'll give you credit in the course, even for your assignments and all, because Erickson talks about, let's say, certain types of averaging techniques and average circuit modeling, average switch modeling and all, which is discussed much later in Professor Ramanarayanan's textbook. So Professor Ramanarayanan introduces a concept called a state space averaging. So which is what we'll probably look at in the lecture. But if you understand one, you will see that everything else is kind of related. Everything else is similar. So the idea is that we have, let's say, two different states of this circuit. Individually, we can analyze the states, but eventually we want to get a single set of governing equations for the converter. We cannot say that when the switch is on, I use this set of equations. When the switch is off, I will use another set of equations. But eventually this switch is continuously switching. It is continuously turning on and off. So we need to do some sort of an averaging. Again, we'll see the rationale for averaging. We have two separate circuits. The question is, can we kind of look at an averaged analysis? You have one set of equations when the switch is on, you have one set of equations when the switch is off. Can we use some sort of an averaging of these two equations to get a final set of, let's say, equations to analyze the converter? And what is the implication of this averaging? So the first question is, this is an idea. So you have two separate states, and this, you're switching from one to the other at a very fast pace. You're jumping from one circuit to the other circuit and coming back. While you can independently analyze the circuit, each circuit individually will not give you all the details about the converter. So some information is embedded in, let's say, in this on circuit, some information is embedded in the off circuit. So to get the complete information, we have to somehow intelligently combine these two circuits. So one way is, can we somehow use an averaging sort of a way, method to combine these two circuits? So if we can use averaging, then what exactly are we doing by that method? So understanding what we are doing to combine and what are the implications of that step is important. So again, here the objective is first write the governing equations of the state equations, right? So here you have two energy storage elements, inductor, capacitor. So we'll have to choose the state variables. Again, I am assuming that you understand certain fundamentals, because 90% of you are taking the control systems course. So I understand, or I take it for granted that you know what a state is, what is a state variable, what is the definition of a state variable. Maybe today the time is short, we only have 10 minutes, so I will not delve into the details. Maybe on Monday's class we can have an in-person discussion where we can focus a little bit more on the fundamental. That will also give you some time to review the fundamentals and come back, so that we'll have a deeper discussion. But at least if you're not clear, this is the time to go back and revise and come back. So you have to have an understanding of what do you mean by a state, what constitutes a state variable, and can you what all can you potentially choose as state variables in this circuit, right? So here I'll give one set of state variables, which is the inductor current and the capacitor voltage. But why am I choosing them as state variables, right? Are there other choices for state variables? So all these questions I'll ask on Monday and we'll have a deeper discussion. But for today, I just want to show you the procedure and then we'll discuss it in detail on Monday. So I'll take maybe 5 more minutes to tell you the procedure. Is that okay? Or are there any questions or comments at this point? Siddhartha, is it clear what we are going to do?
Yes, sir.
Bharat, can you comment? Is it clear?
Sir.
Yeah. Vandana?
Yes, sir.
I'm just calling a couple of representatives, but the point is that if any of you have a doubt or if any of you are not clear, just speak up. Okay. So here I am choosing the inductor current and the capacitor variable and capacitor voltage as my state variables. The choice of state variables and some fundamentals we'll discuss again on Monday. So I'm writing my state equation. So state equation is written in the form x dot is equal to ax plus bu. So x dot, if x is a state variable, x dot refers to dx by dt. So that is why the state equations are written in the form x dot is equal to ax plus bu. So I'll have to write the expression for di by dt and dv by dt. And then there is an output equation. So here my output is the output voltage. So I have an output equation. So these are my state equations and the output equation. And with the state equations and the output equation, I can get the complete information about the system, or I can completely represent the system using this set of equations. And you revise the fundamentals and come back. I'm sure Professor Jayant would have covered this in the control systems class. We'll have a brief discussion on Monday. So now let's derive these. So the first step was derive it individually for the on circuit, individually for the off circuit. Right? So we'll take the on circuit, and let's try to write the expression. So again, it's very simple. All you need to apply is fundamental Kirchhoff's voltage law and current law. So the governing equation can be obtained, the differential equation can be obtained if you just apply KVL, KCL. That's all. Any circuit that you take. So here you can go around the loop and you can write the KVL, that is Vg is equal to LdI by dt plus the capacitor voltage. That is one expression. And so you can go around the loop. There is a loop here and you can write the Kirchhoff's voltage law. And there is a node here. So you can write the Kirchhoff's current law. That is IL is equal to IC plus I output. IC is nothing but CdV by dt. And I output is nothing but V0 by R. So you can right. So one is the Kirchhoff's voltage law. The second is the Kirchhoff's current law. The Kirchhoff's voltage law across the loop, Kirchhoff's current law at the node. And when you write that, you can rewrite that in the form of the state equations. So here you have the LdI by dt. So you can find what is dA by dt. Again, here you have CdV by dt. So you can find what is dV by dt. That's all. So these are your state equations. So just by KVL and KCL, you can write your state equations. And here my output equation, the objective is to express the output as a function of the state variables or the input variables. So here my output is nothing but Vc. So I can just say V0 is equal to Vc. So again, the state variables, the objective is to express it as a function of the state equations. You are expressing x dot as a function of the state variables x and the input variables. So here you see that IL is expressed as a function of the state variable Vc and as a function of the input variable, which is Vg. And here again, this is another state variable. This is expressed as a function of the state variable IL and state variable Vc. There is no direct dependency on the input quantity. And here again, this is same as the state. We have chosen the output quantity as the state variable itself. So these are your state equations and output equations when the switch is on. Likewise, you can derive it when the switch is off. Again, write KVL and KCL, and you will get your state equations and output equations. So once you get your state and output equations, when the switch is on, when the switch is off, now our job is, let's say, how can we get a single set of equations that is representative of the behavior of the circuit? I am interested in understanding the time domain variations of these state variables. I want to see how these state variables are going to evolve in time. I want to see how my output variable is going to evolve in time, right? So I need, but these individual expressions are not representative of the reality. They are only representative of a part of the picture. But I want to know finally in the buck converter, how is the current going to evolve in time? How is the voltage going to evolve in time in a small signal sense? So for that, I have to combine these in some sense. So here I'm just formally writing, right? So x dot here refers to, let's say, dA by dt, dV by dt. It's a column vector. X dot is dA by dt and dVc by dt. So this should be IL by dt. And then, yeah.
Sir, here we shouldn't consider small ripple approximation.
We'll come to that. So right now, I'm just using the instantaneous quantities. Let's assume that these are instantaneous quantities and I'm writing this equation. So later on, we'll get to the point of any approximations. Right now, I have not done any approximation. I'm just taking that these are instantaneous quantities and these governing equations are valid. Whether you apply small ripple approximation or not, these are valid. Because finally, I don't care about the switching ripple, which we'll see eventually. But I do care about some, let's say, perturbations and things like that. So I cannot say that I'll ignore all the ripple in the output voltage, because I'm actually interested in some low frequency response or some small perturbation, which is what you're doing in the lab also, right? You're injecting a perturbation in your duty ratio, which is causing a variation in your output. You're trying to measure that variation in the output. So that is also in some sense a low frequency ripple. It's not the switching ripple, but it's some low frequency outcome because you injected a disturbance. So that is why at this point, I don't want to introduce terms such as small ripple approximation. We'll just use instantaneous quantities. We'll see why it is eventual.
Yes, sir, but if we use small ripple approximation, dVc by dt will become 0. So one of the state variable.
Yeah, that is also, I mean, then if everything is DC, then there is no dynamics, right? If everything is fixed, there is no dynamics.
Yes.
So here, these are instantaneous quantities, and later on, we will, for the last signal part, we'll apply. I mean, we'll look at the average values or the steady state values, and we'll see, we'll invoke that also. You will see that this di by dt, dv by dt will go to 0 when you're looking at the large signal part of the puzzle. When you're looking at the small signal part, there will be these dynamics. You cannot, I mean, those dynamics will be present. So we'll see that. That is coming up in the next slide. So yeah, here you can formally write it in the, I mean, the state equation and the output equation format. X dot is equal to Ax plus Bu. Your Y is equal to Cx plus Du. In this case, the output is not related to the input, so there is only Y is equal to Cx kind of a expression. And you can find what these A matrices, B matrices, and Q matrices are, at least according to this notation. And that is straightforward. You can find that from this set of equations. And A1 refers to, let's say A1, B1, Q1 refers to the matrices or the vectors when the switch is on from these equations. A2, B2, Q2 refers to the matrices or vectors in the from this set of equations. So you can, and the same procedure you can use for any converter, buck boost, buck boost. There is no difference. You have done the same thing for boost converter. And then now the challenge is, okay, we have these two sets of state equations, but we want to represent the converter through a single equivalent dynamic representation, which is valid for both on time and off time. Right now I have separately, I have set of expressions that can, let's say, that are valid for on time and separately valid for off time, but I want a single representation. So that is where we use this idea of state space averaging. Here, what we are doing is referred to as state space averaging, but there are several equivalent approaches. You could do what is referred to as a waveform averaging. You could do what is referred to as a circuit averaging. You could do what is referred to as a switch averaging. So these are all techniques that were developed in the 70s and 80s. Various kinds of averaging techniques. Everything will lead to the same kind of a result. So the idea is you can take the waveform. There is a waveform during on duration, off duration, and then you can use averaging on the waveform. Or you can take the circuit itself and you can try to come up with an averaged circuit model. Or you can just take the nonlinear elements, which are the switches, and you can try to sort of average out the impact of the switches. So these are all equivalent techniques. And I think in SMPC, you will learn some of these competing techniques. So a large part of SMPC, I think, will cover the different ways of modeling DC-DC converters. So here we'll only look at one way to model. I want you to understand one methodology, but then you will be able to appreciate the equivalences between methodologies and all when you take the switch mode power conversion course. So here what we are doing is some sort of an averaging. That is, we know that this circuit is valid for DTS duration and this circuit is valid for 1 minus DTS duration. So we do some sort of a time averaging. That is, we write an average state equation using the individual state matrices. That is, A1 is applicable for DTS duration, A2 is applicable for 1 minus DTS duration. Likewise, B1 is applicable for DTS, B2 for 1 minus DTS, Q1 is for DTS, Q2 for 1 minus DTS. So we combine them. Basically, we are doing a time averaging of the matrices. And this is referred to as an averaged equation. Again, we are running out of time. So on Monday, we'll try to understand what exactly we are doing by this averaging. So this is a procedure which I've just explained. You're also taking my words for granted. But what exactly are we trying to accomplish by doing this averaging? And how exactly these equations are going to describe the how the state and output variables, how they are going to evolve in time. So think about that, read about state variables and state space basic, let's say state space representation before Monday's class, and we will discuss the rest on Monday. So we'll stop for today. Any last questions? I can take a couple of questions now. Yeah, if there are no questions, we'll close the discussion. You can tell the students who might have missed, right? I mean, let them at least discuss with you in terms of what we discussed. And if they want, I mean, let them come and talk to me also. But at least I intentionally did not record the session because you guys should have informed me about the conflict, right? I would have done something to help you guys. But if you have not informed, then that means that you already were planning to skip the class or the lab, one of that. So then that's a choice that the students have made. But if you inform the instructors, we'll try our best to accommodate your needs and concerns. But other than that, we cannot do anything because we expect the students to attend the classes. And this is the first time, I mean, I have been here for a few years now, but this is the first time your batch is the first batch where I'm seeing such a terrible drop in attendance. So in all the previous years, I mean, most of the students, there'll be one or two students who are missing out, but again, the same students will not be missing every classes. One or two students will be missing, and that too occasionally. But this is the first time that I'm seeing a very terrible performance in terms of attendance, and that is precisely why I did not want to record the meeting. If the students are serious about the course, then they'll figure out a way to attend, or they'll inform the instructor about the needs that they want. If that is not being done, then I also take it that that is the level of interest from the student side. So, but at least inform your friends, right? That this is not good. I mean, missing these many classes, it is not good. And this probably in the last few years, this is the worst that I have seen.
Excuse me, sir. I have one doubt.
Hmm.
Sir, in class, not in the online class, in offline class, we drew the ripple for the output voltage, and in that we actually showed that the ripple is actually going below the x-axis, but nowhere the means I believe that the output voltage is always positive, right, sir?
Correct. I only drew the ripple. The thing is, the actual output voltage is the steady state average plus the ripple. So which will be positive. But what I drew was only the AC component, the ripple component.
This will be means we have to superimpose it on the average
VC
voltage.
Yeah. So if you remember, if you look back at your notes, I would not have called it VC. I would have called it delta VC or delta V naught. When I drew that waveform,
okay,
I clearly remember that I marked it as delta V naught. So the instantaneous output voltage, the notation that I'm using is VC or V naught, depending on whether it is a capacitor voltage or not. So this V naught is nothing but the average value, capital V naught plus the ripple, delta V. So I only drew the delta V, the ripple component. So that should clear the confusion. So the ripple component is always an AC component, but when you superimpose with the output DC quantity, the net waveform will always be positive. It will not go negative.
Okay, thank you.
Yeah. Any other points?
Sir, the waveform that we draw in this class is also delta VC waveform, sir.
Yeah, what I drew today, that is also delta V.
Yes.
Because the average.
Sir, I have a question.
Go ahead.
Sir, about the inductor and capacitor values, we need certain values to be in CCM or to make ripple current to a fixed value. But why do you want to keep the frequency of oscillations very low?
We don't want oscillations. It is not that we want to keep the frequency of oscillations low. So you think I'll give one example. Maybe. So let's take a simple circuit, okay? Let's say you have an LC circuit or LCR circuit. So let's say I'm exciting it with a pulse or a pulse train, which is what we are doing in our buck converter. So now when you are exciting it with a pulse train, you can analyze this circuit, right? You can analyze the second order circuit. You know that there are going to be oscillations. All that is fine. So maybe before even going into pulse, let's look at step. Let's look at step. So when you look at a step, when you give a step excitation, the resonant frequency is going to get excited. You are going to have an oscillatory response also. So now the question is, there is a particular frequency for that response, right? So that frequency is defined by the cutoff frequency of this LC filter, 1 by 2 by root LC. So now in our PWM converters, we are continuously switching. So there are two frequencies at play. One is the frequency of this, let's say LC filter. The second is the switching frequency. If let's say the frequency of the filter is comparable, or if it is higher than the cutoff frequency, or if it is higher than the switching frequency, then so at this point, what I'm doing is it is like a step excitation to the system, right? When the switch is turning on, when you're applying a voltage at the pole, it's a step excitation to the system. So if the resonant frequency is higher than the switching frequency, then the current or the voltage, it can ring completely within this interval. So you will see a highly oscillatory response. And that is the principle that is used in resonant converters. So in resonant converters, the resonant frequency will be comparable to the switching frequency. So you want the components to resonate. But in pulse width modulated converters, what we do is we don't want to make use of this resonance phenomena in power transfer, but rather we want the components not to resonate. So if we don't want it to resonate, then the resonant frequency should be much lower. That is, it may still be an initial part of a, let's say, of a resonant kind of a oscillation. But the thing is, you're only looking at the very initial part. The frequency is so low. It may eventually, it would have gone into an oscillation if you had not changed the state again. If it was only a step response, eventually it would have become a sinusoidal response, but you're only seeing the initial part, which can be approximated as a linear approximation by assuming a step voltage. So the power transfer is not happening because of resonance, but there are certain type of circuits that actually take advantage of this principle, and they are called as resonant converters. And you may study about those converters either in SMPC or advanced power electronics. So these circuits, they are oscillating, but the thing is, before we can see the effect of those oscillations, we are continuously switching. So the switching frequency is way higher, that you're only seeing the initial part, which looks like a linear variation.
Okay, understood.
Sir?
Yeah.
In delta VC, we are observing the waveform. If the average is much lower, and if the graph goes below the x-axis, means if it goes to negative, will there be a case where it is going to negative?
What will happen to your converter if it goes negative? Let's take maybe an easier example. I'll only give one counter example, because when you put forth the hypothesis, you only need one counter example to prove or disprove. So here, let's take the boost converter. Let's say that by your argument, the voltage has gone negative. Then what is the implication on the circuit? What is the voltage that you're applying? When the device is on, the diode is supposed to block the voltage, right? But if you have a negative voltage, the diode will never be off. So you will have some sort of a short circuit. That is not a desirable condition. So your voltage will never go negative. I mean, typically the current can go very low because you are changing the load resistance and all. The current can go very low, but the voltage, you typically don't design it to be very low, because the application may demand a certain voltage, right? Many of the, whether you are using it to power say ICs, whether you are using it to power batteries, whether you are using it to power, let's say, whatever other component, there is a requirement in terms of voltage. And you choose the ripple to be much smaller than the voltage. Then only the small ripple approximation itself is valid. And I told you that typically that ripple will be 1 to 2%. So if the ripple is only 1 to 2%, howsoever small your voltage is, it is only 1%. So you are never ever going to go into a negative voltage phenomena. And if you go to a negative voltage, then many of these converters will not work also. I mean, they cannot support negative voltage.
Yes.
Any other questions? Okay, so thank you for attending on a Saturday, and hopefully, I think we have been able to cover some ground today. So we'll meet again on Monday, regular class hours. Bye. Take care.
Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank you.